Okay, so I'm going to start working on outputting executable files for Windows. Windows uses this format called PE format, which stands for Portable Executable. And the entire thing pretty much is documented in this document that I've got open here. This is a PDF, but it's just on their documentation website. So I thought I would just basically go through this document and just do what it says. I know ahead of time from doing this at least once before that there are a few other documents that are useful to reference, so I've got them open up here already. Um, so yeah, we'll just go through it and try and generate a P executable file, portable executable file. So this specification describes the structure of executable image files and object files under the Windows family of operating systems. These files are referred to as portable executable (PE) and common object file format (COFF) files, respectively. The document specifies the structure of an executable image files and object files under the Windows family of operating systems. These files are referred to as portable executable and common object file format files, respectively. The name portable executable refers to the fact that the format is not architecture specific. Certain concepts that appear throughout this specification are described in the following table. So this is just a description of some of their terminology. File pointer is just, a location within a file. Object file is just in reference to inputs to the linker to produce an image. Relative virtual address is basically a virtual address, so a virtual memory address with the image base subtracted from it. So you can basically just assume the base is 0 and just refer to memory from 0. And then sections are the basic unit of code or data, and this is basically where you put all of your data that you've described in the headers. And then a virtual address is the same as an RVA, but you basically add on the image base. So this is where this would be like an actual address in virtual memory. So the following list describes the Microsoft PE executable format with the base of the image header at the top. The section from the MS-DOS to compatible exe header through to the unused section just before the PE header is the MS-DOS to section and is used for MS-DOS compatibility only. So that's basically talking about these things here. I guess down to here. So this is for MS-DOS compatibility only. The only thing that we really care about here is the compatible header part and the offset to the PE header, which is this one down here, and it must be aligned on an 8-byte boundary. Then after the PE header we have section headers to describe where all of our sections are, and just, yeah, more data basically. So we'll go through all of these as we go through the document. So the PE file header consists of a Microsoft MS-DOS stub, the PE signature, the COFF file header, and an optional header. A COFF object file header consists of a COFF file header and an optional header. In both cases, the file headers are followed immediately by section headers. So the MS-DOS stub is for image only, and since I'm going to be making an executable file that I expect the loader to actually load into memory and execute, I will need to provide this because I'm making an image. The MS-DOS stub is a valid application that runs under MS-DOS. It's placed at the front of the exe image. The linker places a default stub here which prints the message, "This program cannot be run in DOS mode." When the images run in MS-DOS, the user can specify a different stub by using the stub linker option. So this is just talking about the MSVC linker. And this is what the MSVC linker does, is it prints this message if it's run in DOS. As far as I can see, pretty much everyone else just copies this. Technically, it says that you're supposed to have a valid stub application, but I am just going to completely ignore this and do the minimum without actually providing a valid application, because I don't expect these things to be run in DOS 2.0 anytime soon. So at location OX3C, the stub has the file offset to the PE signature. This information enables Windows to properly execute the image file even though it has an MS-DOS stub. This file offset is placed at location 3C during linking. So at byte 3C, we need to basically just put the offset within the file to where the PE signature starts. And my plan is basically to put the PE signature directly after this. So if this is a 32, I think it's a 32-bit number. So, we would have 4 extra bytes. So we would go, C, D, E, and F, which means that the PE signature could start at 40. And 40 divided by 8 would be 8, because 40 is 64. So 64 divided by 8 is 8. So that means it aligns on an 8-byte boundary. So we're just going to put the number, hex 40 at this location. So signature, image only, after the MS-DOS stub at the file offset specified at offset 3C is a 4-byte signature. Yeah, so it is 4-byte signature that identifies the file as a PE format image file. This signature is PE with 2 null bytes after it. Then at the beginning of an object file, so this is object and image, we need the COFF file headers. At the beginning of an object file or immediately after the signature of an image file, is a standard COFF file header in the following format. Note the Windows loader limits the number of sections to 96. So this is basically, we're filling out our first struct of information and just directly putting it into the file. And there are a few places we're going to have to jump around in this document to get things like constants. So for example, down here we've got machine types, so we'll want to use machine AMD64, which is this hex value that would go into this machine field here, for example. So I think this is enough to start. Basically, we need an MS-DOS stub, followed by a PE signature, followed by a COFF file header. And when it comes to the MS-DOS stub, it's useful to know that there's this DOS MZ executable, which is the executable file format used for exe files in DOS, and it can be identified by the ASCII string MZ at the beginning of the file, which is the magic number. So basically, our DOS stub is going to be, the bytes MZ followed by enough padding to get to byte 3C. Then the offset 40 in hex, followed immediately by the PE signature, followed immediately by the COFF file header. So the only reason I've brought this up is because this MZ magic number isn't actually documented in the PE format document, so you have to go looking elsewhere or look at existing PE files and see what they do, and they pretty much all you'll see that they all have this MZ at the beginning of them. So if we just go into the project and start this off, so if I go into main, I think I'll write the usage first. So the idea will be that we create a new image, which will be p.new. Then in the image, we'll basically want to be able to give it sections and things, but right now we don't have sections. But we'll need a text section to put the generated code. So we would have something like image sections equals append to image sections, and then we would have some, p.section struct that can go in here. Then we would need to be able to get the bytes back to write out to disk or somewhere. So we could, for example, say if error equals os write file. I think write file takes a name, so this will be test fin.exe maybe. Then we're going to take some bytes. So here we would want to say, for example, image.bytes. Then we need permissions, which don't really matter for Windows, so we'll just say mode, I think it's mode perm, maybe. If there was an error, we'll os.exit1, and we'll print the error. Otherwise, we should end up with an executable file. So we just need to fill out this API, which is basically just the new function and the ability to append sections. So we'll create pe.go, package pe. So we'll have type pe, I guess. And in here we'll have sections. So we'll have a slice of sections. And sections are going to have data, which is just going to be bytes. So we would put our generated machine code into a section and then use that when we're getting the bytes out. So we need a func new. This will be a constructor for PE. So we'll return new PE. And we also need bytes. So this will just return the bytes that are generated. Maybe we'll just do var b is bytes, slice, and then we'll just return b for now. So this should do nothing. Just import those things. Okay, so this just does what I left it off with last time. And now we need to start generating some bytes. So the first thing is the MZ followed by enough padding to get to 3C. I don't know what 3C is off the top of my head, so programmer hex. So if we've got 3C minus 2, so that's 3A. So after the MZ, we need 58 0 bytes of padding to get to 3C, and then we'll put in the 4 bytes offset. So yeah, okay, and then that gets us to 40, which is 64 bytes in. So we'll just say b equals append to b. We'll have the m followed by z. This is the ms. Well, I suppose I'll just mark these sections. We've got MS-DOS stub. This one is the magic number. We'll just call it magic. Then we need some padding. So we've got append to b. We'll just make some slice of 0 bytes. We need 58 of them, and we'll just spread them all in. So this is padding until PE signature offset. Let's see. Oh, this should be 58 here. Okay. So this is the MS-DOS stub. Then we need a P signature. Oh, sorry, no, we don't need the PE signature yet. We need the offsets. So here we'll need to the file format is in little endian. So we'll do binary dot little endian dot append uint32. So in here we'll basically just do OX40 because that will be the byte immediately following this this offset. So this is the P signature offset. Then we got the P signature which is just PE followed by 2 zeros. So we'll just take this thing here. We got PE followed by 2 0 bytes. This is the signature. Then we need a COFF file header. So the COFF file header is basically just this struct that it's describing here. So at offset 0, we've got a word, which is the machine field. Then we've got the number of sections, which is also a word, followed by, however many other sections here. So I think if we just copy these out. So this is the COFF file header. Okay, so we've got all of these fields here. So we're going to need to do 16 bits, 32 bits, 16 bits. This is probably going to get a little bit tedious typing this out all the time, so I'll just have, for example, little endian 32, and we'll just assign this up here. So we're going to do little endian 32 is equal to this one, 16 is equal to this one. So we've got word followed by double words until the size of optional header. Let's just do this, B, and then something. So this is a word, so that's 16, 16, and then size of optional header is where we turn back into words again. So machine is actually down in here as this constant, so we'll just copy this constant name out and put it up here. This is equal to this, and we'll just, the machine identifier, I guess, is that constant. So because we're making an x64 executable here. Then we've got the number of sections. So this indicates the size of the section table, which immediately follows the headers. So I'm only going to have a text section right now, but this is basically just going to be the length of the sections slice up here. So we'll say, change it into a uint16, the length of p.sections. Now timestamp is when the file was created. I'm just going to leave this as 0. This one is deprecated and should be 0. This one's also deprecated and should be 0. So the timestamp, pointer to symbol table, and number of symbols can all be left as 0 here. Then we've got the size of optional header. So the size of optional header, which is required for executable files but not for object files, this value should be 0 for an object file. For a description of the header format, see optional header. So we don't actually know the size of this yet, so we'll just put a syntax error in here. And then we've got characteristics. So characteristics is the flags that indicate the attributes of the file. For specific flags, see characteristics. So we are basically just going to have to fill out all of the flags that apply to our file. So we don't have any relocations right now, so we'll use relocs stripped. That is 1. This is going to be an executable, so that's 2. We don't have line numbers, so this one is 4. Oh, this one is 0, so I guess we don't need to put this one in, actually. Okay. So executable is fine. This one is fine. We don't need this one. We don't need this one. Obsolete. Don't need this one. Application can handle greater than 2 GB addresses. Since this is an x64 executable and we want to use things like the address randomization, I can't remember what it's called. There's some security feature for randomizing the base address of the image in memory. But we want to be large file or larger address aware, and this is just going to happen for most of what we're doing anyway, because we're using RIP relative addressing and things. We don't need this one. This is deprecated. Machine is based on 32-bit word. That's not true. We don't have any debug information, so we should take this one. Removable run from swap. If the image is on removable media, fully load it and copy it to the swap file. Don't need that. Net run from swap. Don't need that either. Image is a system file, not a user program, so I assume that's more like a kernel thing. The image file is a dynamic link library. Such files are considered executable files for almost all purposes, although they cannot be run directly run. So PE32, this is called PE32 and 32 plus. PE32 is the 32-bit version, and PE32 plus is the 64-bit version. They cover object files, executable files, but they also cover DLL files. So we don't need this one. Ours is an executable. File up system only should only be run on a uniprocessor machine, okay, and this one is deprecated. So we only need these flags as far as I can tell. Maybe I'll just check if I've missed any. 0, 0. I think that's it. I'm sure if we've missed any, Windows will just error anyway. So this is characteristics. Let's see. So we'll do const characteristics, or this will be COFF characteristics. So let's just put these into here and OR them together. Okay, so we've got COFF characteristics. We don't want, I'll put -1 in here. Okay, so we don't know what size of optional header is just yet. Then we get onto optional header. So this is only for images. Every image file has an optional header that provides information to the loader. This header is optional in the sense that some files, specifically object files, do not have it. For image files, this header is required. An object file can have an optional header, but generally this header has no function in an object file except to increase the size. Note that the size of the optional header is not fixed. The size of optional header field in the COFF header must be used to validate that a probe into the file for a particular data directory does not go beyond size of optional header. For more information, see COFF file header. Okay, optional header. The number of RVA and sizes field of the optional header should also be used to ensure that no probe for a particular data directory entry goes beyond the optional header. In addition, it's important to validate the optional header magic number for format compatibility. The optional header magic number determines whether an image is PE32 or PE32 plus executable. So we need this magic number for PE32 plus, which is 64-bit. PE32 plus images allow for a 64-bit address space while limiting the image size to 2 gigabytes. Other PE32 plus modifications are addressed in their respective sections. The optional header itself has 3 major parts. So we've got the first part is the standard fields, then we've got Windows specific extensions. So the COFF, is this COFF or is this just something else? I don't know. Oh yeah, so fields that are identified for all implementations of COFF, including Unix. Then we've got Windows specific, basically like extensions to this COFF format, I guess. And then we've got data directories, which is just some tables that tell Windows where to find the data for different information in the executable. So the way these tables work is that we have the offset. If there's a slash here, then the first number is the 32-bit version, and the second number is the 64-bit version. And that's just because between PE32 and 32 plus, sometimes the fields, some fields have been removed or added, I think. So I guess then that basically the size of the optional header is going to be at least this offset, because that's like the minimum ending section offset of the optional header, plus however big that is. So the standard fields, okay, I guess we'll just skip ahead and just see how big the optional header can actually get. So this is the data directories, and right now, so we could end up with data directories that go up to 232 as the offset from the beginning of the optional header, plus 8 bytes. So we'll end up with 240 bytes. So this is going to be the size of the optional header. Which will be part of the optional header standard fields, I think. Size of headers, size of optional header, where is that? Let's have a look for it. Oh, size of optional header is the one I set to -1. Okay, so this one should be 240. So that's the size of the optional header. Size of optional header is 240 bytes. So I think that covers all of the COFF file header. So we'll start on the optional header now. So I've read all of this. Basically, I need to start it with the magic number, which is part of the standard fields here. So we've got magic. So I think what I'll do is these are the optional header standard, and P32 contains this additional field, which is absent in P32 plus following base of code. So for P32 plus, we can basically just take these fields here. So we'll just make these comments so that we can see what they're actually describing. So this is the optional header. What was this called? Standard fields. Okay, so we're going to need word followed by 2 bytes. Let's just take some of these. So we've got a word followed by 2 bytes, which I'll do as just a regular append. Then we've got 2, 3, 4, 5 D words. So the rest of them are D words. Major linker version is, okay, that's actually, all right, we'll change that to append 0, and then 1, 2, 3, 4, 5. These are all D words here. Okay, so the magic number for PE32 plus is this. Then we've got major linker version and minor linker version. Oh, let's just check the magic number. Yeah, so 20B identifies as a PE32 plus. So we've got linker major version and minor version, which we'll leave as 0. Then we've got size of code. So the size of the code text section, or the sum of all of the code sections, if there are multiple sections. So from what I remember of these size of fields here, it's not really specific about whether it's talking about on-disk size or virtual memory size. So when the Windows loader takes our file and it loads all of our sections into memory, those memory sections can be bigger than the sections on disk. And so it doesn't really specify which size it's talking about here. But from what I can gather from looking at other PE files in the past, the size of code seems to usually be set to the size of the code sections on disk. Size of initialized data is also disk. So these two are disk sizes. And then size of uninitialized data doesn't actually exist on the disk because it's uninitialized data. It's the BSS section. So for this, what typically happens is that the linker just puts in the virtual memory. So this is the memory size instead. Now I don't have any initialized data right now or uninitialized data right now, so I'm only going to put size of code in, but I'm going to follow what other linkers seem to do and do disk size, and then memory size for this one. So the address of entry point is the address of the entry point relative to the image base, where the executable file is loaded into memory. Okay, so this is basically the memory, the virtual memory address, or the RVA address, RVA. This is the relative virtual address where I want code for the program to start executing from. So this would be, for example, the first byte of the main function. But since I'm not tracking where those bytes are, and I only have one function and one code section, I'm just going to make this the start of the code section. And then base of code is the address that's relative to the image base of the beginning of code section when it's loaded into memory. So this is basically the RVA of the first code section. So for the moment, these two things are actually going to be the same for me, but they don't have to be the same. This is always the first code section RVA, and this is always the byte that you actually want to start executing at in virtual memory. So size of code. we don't actually know what it is yet. But by the time we run this bytes function here, we should already have all of the sections. So we could just loop over all of the sections. And then we would say, for example, add up the size of those things. So this would be, for example, so size of code is going to be a uint 32. Then we can put size of code in here. And size of code for now can just be plus equals section dot data. This will just be the byte length of this. But this is the size of the code section, or the sum of all code sections if there are multiple sections. So I'm pretty sure that Windows doesn't really use these necessarily. I'm not sure. Maybe it does, maybe it doesn't. But we'll just leave it as this for now. This might be aligned to some, needs to be padded, I can't remember. We'll come back to it later if it does need to be. These two can stay as 0. So we've got 0 here and we've got 0 here. The address of the entry point is the RVA of, I'm just going to do it as the RVA of the first section, but right now I don't have that, so we'll just put -1 for all of those. Then we've got optional header Windows specific fields. So this is Windows specific fields. So here we have image base, section alignment. It's okay, yeah. So here's the section alignment and file alignment. We'll get to these in a minute and go back and fix some things. Okay, there's quite a few fields here. Okay, let's just take these first ones. So we've got file alignment, section alignment. Then we've got, yeah, so this is image base here. Let's get the rest of these. Okay, I think that's all of them. So I've got a total of 21 fields here. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay, so that's all of them. So image base, let's just do equals, I don't know, LE32 for now. We'll just do 0 on all of them. So image base for 64-bit is actually going to be 8 bytes. So I guess I should take in LE64 over here. So image base LE64. So this is 64-bit value saying the preferred address of the first byte of the image when loaded into memory must be a multiple of 64K. The default for DLLs is this, the default for CXEs is this, NT, XP, etc, etc. I think I will just take this one then, since that seems the closest. Next is section alignment. The alignment in bytes of sections when they are loaded into memory, it must be greater than or equal to file alignment. The default is the page size for the architecture. So the page size for the architecture, so Intel architecture here is going to be 4K or 4 kilobytes. So I think I'm going to store these in here actually. We'll say section alignments. And we've also got file alignment. These can be integers. So file alignment, the alignment factor in bytes that's used to align the raw data of sections in the image file. The value should be a power of 2 between 512 and 64K inclusive. The default is 512. If the section alignment is less than the architecture's page size, then file alignment must match section alignment. So section alignment we're going to set to just be 4K. I'm pretty sure that's 4K. Let's just check. Calculator. Let's go to hex. 1000 is 4 kilobytes. And then file alignment, I know hex 200 is 512, so we'll leave it as 512. I guess, so if every section in the file has to be aligned to, you know, this file alignment, then if we make it too big, we're just going to end up with a load of 0 bytes that are just taking up space. So we'll leave it as 512 to have the most granular sections that we can. And section alignment, this is 4 kilobytes for the architecture page size. If the on-disk sections are going to be padded to this alignment, then that means size of code should probably be the sum of the padded sections. So if this was just 100 bytes of data, we'd need to pad it with 412 bytes of zeros. So even if we just had 100 bytes of data, the actual size on disk would still be 512 because it has to fit in that file alignment. So we'll probably just have some function here called padded. So this will take in some value, which it will then, we'll have a value and an alignment, and it will take the value, and then, which is the number of bytes, and then it will just add however many onto that as the return. So for example, if we had n, so n will be, for example, how many times value goes into, or how many times alignment goes into value. And if it doesn't go into value cleanly, then we need to add 1. So if value mod alignment isn't 0, we'll add 1 to n. And then we'll return the alignment multiplied by n. So that should, I think, give us the correct values. So we should be able to say, for example, the size of code plus equals padded to PE file alignment. And that should do it, I think. Let's just test that. So we got, let's go over here. I'll comment out this stuff that I've done here. We'll do a print line of padded, let's say 100 to 512. Yeah, so because it's 100, it goes to 512. If I go over 512, so 513, this should pad up to 1024. Yeah, okay, that's correct. Okay, let's carry on with generating this PE file. So the section alignment is going to be p.section alignments. I'll need to change that to uint. What is this? Uint 32. This one also uint 32. This is p file alignment. Then we've got major operating system version. Okay, so this is the major version number of the required operating system and the minor version. So as far as I understand, Windows won't actually care too much about these as far as like preventing you from running executables. But it may have something to do with it putting in like compatibility shim code and things like that. But these operating system version numbers aren't really documented anywhere officially by Microsoft as far as I can tell, other than this operating system version page, which is from the online documentation. So for example, Windows 11 is actually 10.0 with this asterisk next to it. Going all the way back to Windows 2000, which is 5.0. But for other PE files that I've actually looked at, a lot of them use 4.0, and they stopped listing them here. So instead of this one, there's actually this wiki page which has a proper list on it. And so from here we can see that 4 is actually this NT, Windows NT, Windows 95. So I don't think this is really used for much important as far as like actually stopping running executables and things goes, maybe, but we'll just copy what the other PE files do and put in 4.0. For the operating system, at least. So this is 4.0. Then we've got major image version. This is the major version number of the image. I'm just going to leave those as 0. And then we've got subsystem. So again, subsystem isn't particularly well documented, but you can find it in this subsystem documentation for the MSVC linker flags. And if we go down to this table here, there are basically these different subsystems. So the only two that we actually care about now are console and Windows. Console is used for when you need a console application. So in this case, when you start up your application, Windows will it will start conhost as the sort of terminal thing. It will use CMD, for example. That gets to use, for example, CMD as shell and everything. But it will start up conhost, attach it to your program, so you get the console handles and everything. With Windows, it won't start it up. So if you want a console, in this case, you have to create the console and attach it yourself. Basically, if you want a console application, you need the subsystem for console, and the minimum for that on x64 is 502, so 5.2. And then for Windows, x64 is also 502 as the minimum. It says the default here is 6. I assume that that's the default that the MSVC linker puts in now, but we'll go for the minimum here, which is 5.2 for x64 for the subsystem version. So we'll say 5.2 here. Then we've got Win32 version value. So let's just close this one. Oh yeah, I think as far as like actually telling Windows about operating system versions you support, you should really do something like embedding a manifest file. And in that case, you can do things like telling it what your program supports, basically. There's a supported OS here, for example, where you put in the GUIDs for these different operating systems to basically say, if you're running on one of these, you don't need to sort of put in these compatibility shims and things. So I'm gonna not do this for right now, but later on when I'm generating executables a bit more sort of properly and fully featured, this is something I'd want to put in so that I don't get odd behavior from various APIs. For example, returning fake version numbers and things to keep backwards compatibility. So the Win32 version value is reserved and must be 0, so that's fine. Size of image is the size in bytes of the image, including all headers as the image is loaded in memory. It must be a multiple of section alignment. So if we are loading into memory, including all headers, so I assume then that that's basically pretty much everything so far plus the sections. So size of image is probably something we'll have to calculate up here as well. Size of image. This is also Win32, I think. So the size of image. We've got size of optional header. That is the size of optional header plus all of the data directories that are going to come after this. So we'll need to include this in here, I think. It may be that what we can say is just, we've got the COFF header plus the size of so optional header already covers all of this stuff. We need to know the size of all of this stuff up here. Does it include the MS-DOS stub? It's the size of image loaded in memory. So we could, for example, say that it's, we got 64 plus, okay, so we got, how big is the COFF file header? COFF file header is 20 bytes. Plus, we've got 60 bytes here, or 64 bytes. Yeah, so we got 60, 62, 3, 4, 5, 6. 66 plus 20, as far as I can tell, so 86 here. Maybe what we'll do then is just say, for example, the size of stub and COFF could be 86, maybe. I'm not sure exactly if these are supposed to be included or not, but it's not going to make much difference to the padding and things here, so we'll include it for now and fix it later if it's not supposed to be there. So size of stub and COFF is this much. So if we add this and the size of optional header together, And then we end up with, let's see, it included headers as the image is loaded into memory. Okay, so this is all of the header sizes. So we've got optional header, we've got stub and COFF. And then I think the data directories are... Well, I think we'll come back to this one because we'll have to look at the size of maybe data directories as well. I'm not sure exactly. I think... Maybe we'll just say for now that size of image is going to be the size of this plus the size of optional. And then we're going to add on the size of each section's code padded out to the section alignment. So this might do, and then we just have to pad this. So we'll say padded is this to PE dot section alignment. Because each section is going to be loaded into memory, so this counts towards the image size. And maybe we'll just redo this again instead of using the already padded number. So we've got size of image here. This might need to change a bit later, but we'll see. Then we've got size of headers. The combined size of an MS-DOS stub, PE header, and section headers rounded up to multiple of file alignment. Okay, so this does mention MS-DOS stub here, so I assume that it's correct to include that in the size of image. So we'll call this one size of headers. This can be the stub and COFF plus the size of optional. So the size of image starts out as the size of headers, and then we can put size of headers down here. Checksum. The image file checksum, the algorithm, blah, blah, blah. Okay, I'm not going to do that, so we'll leave that as 0. Subsystem, the subsystem required to run this image. So this is basically the execution environment, I guess, that's expected. So this is basically, if it's GUI, we don't get a console attached. If it's a CUI, then we do get a console attached. So these are the only two I actually care about. So we'll just go and put these subsystems down here. So this is 2 and the CUI is 3. And since we don't have any graphical user interface stuff going on right now, we're just going to put the subsystem is supposed to be the CUI. Okay, so DLL characteristics. Okay, so even though this says DLL, I'm pretty sure this applies to us as well. So high entropy virtual address. Image can handle a high entropy 64-bit virtual address space. So we definitely want that one. Let's do const up here. Then we've got dynamic base, so this is that security thing where it can change the base address randomly. I can't remember what it's called now. Address space layout randomization or something. Let's see, NX compat. I think this was related to it was something related to like an execution protection flag. Either way, I think we need to set this one. Isolation aware. Okay, no structured error handling. Do not bind the image. Terminal server aware. I think terminal server aware is needed as well. I think this is related to knowing that you're running in things like RDP, maybe. I think if you don't have this, it might have like some compatibility shims it might insert. I can't really remember. It's something along those lines. So we'll just take all of these. These are going to be the DLL characteristics. Okay, this will equal these, and we'll just all these together. Okay, size of stack reserve. So when Windows loads our executable into memory and starts a process and everything for it, we basically get a stack for our thread. Or every thread gets a stack, and when you create threads, it creates the stacks and stuff. So stack reserve is the contiguous addresses, or the volume of contiguous addresses that will be reserved for use for the stack. But the commit size is how many of those is how many bytes to actually sort of, you know, actually commit memory for that could be used in physical memory, or like paged out or something like that. And then when the stack is used, Windows will automatically deal with things like I think it's a guard fault, so it inserts a guard page, and when it deals with that guard fault, I think it commits more memory from your reserve. So basically, we need to set the reserve. I'm pretty sure that the default size of stack reserve is 1 megabyte, so we may just do that. I can't remember how much 1 megabyte was. But it's not a million bytes, is it? It's actually going to be this one. Yeah, that's 1 megabyte. Yeah, so we need 1 megabyte of reserve, but then we could commit, for example, 4 kilobytes. And then the same thing goes for the heap reserve, so we'll get a default heap for the process to use, and that will be used when functions are called that they need a heap, but they don't get past an explicit heap to use, so we'll use the default process heap. So we'll just set the same for those. Then we've got loader flags, reserved must be 0, okay. Then the number of RVA and sizes. So the number of data directory entries in the remainder of the optional header, each describes a location and size. So this has actually, is variable in the sense that they could extend this in the future, and it has been extended over time. But we'll just put however many tables there are in here right now. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we'll do 16 in here. Okay. And then we basically have this data directories, which is just these structs. So we've got 2 D words here, a virtual address and a size. So this is the optional header data directories. Okay, so each of these is just going to be 2 LE32s. So we do a little endian 32 B, and then some things. So this is basically this is going to be an RVA, and then we've also got a size. So let's just do 0 in these at the moment. So the first one, I guess what we'll do is we'll just take all of the names of these. Okay, so we've got a CLR runtime header, delay import descriptor, then we go up to IAT, then we got bound import, load config table, TLS table, global pointer, architecture, debug, base relocation table, certificate table, exception table, resource table, import table, and export table. So there should be 16 of them here. I seem to have 15. Oh, yeah, reserved is down here. Okay. So for each of these data directories, we'll have this RVA and size struct that we encode here. So let's just have a look at these quickly. So the export table is the export table address and size. Okay, well, don't need to worry about that. Import. I think this is basically if you're exporting things like you need to tell it where the table is. For example, if you're exporting functions or symbols from DLL files. Same goes for import table and stuff. So I don't think I need any of these tables really. TLS for thread local storage stuff, load config table, bound import, IAT. So the import table and the import address table here will be important later on when we do stuff like foreign function interface, at least for FFI to native Windows or like Win32 APIs, because we'll need to ask the loader to patch function addresses into the memory for us when it loads, at load time. Delay import, CLR runtime header. Okay, so I don't really need to fill any of those out. They just need to exist. So that we've got the correct number of bytes here right now, but import tables in particular will probably be, become useful quite soon. So now we've got a section table, which is section headers. So this probably also adds on to the the image size that I calculated earlier. So we've got a size of image here. Each row of the section table is in effect a section header. This table immediately follows the optional header, if any. This positioning is required because the file header does not contain a direct pointer to the section table. Instead, the location of the section table is determined by calculating the location of the first byte after the headers. Make sure to use the size of the optional header as specified in the file header. The number of entries in the section table is given by the number of sections field in the file header. So that was just len p sections. Entries in the section table are numbered starting from 1. The code and data memory section entries are in the order chosen by the linker. In an image file, the VAs for sections must be assigned by the linker so that they are in ascending order and adjacent, and they must be a multiple of the section alignment value in the optional header. Each section header has the following format for a total of 40 bytes per entry. So I think the missing piece for this size of image here is going to be that it's the size of headers plus the length of pe.sections, or it's going to be basically the size of section header multiplied by the number of sections we have. And a section header is 40 bytes. So if we've got size of images, the size of the COFF, stub, and optional headers, plus the number of headers that we've got for the sections, plus the data padded to the section alignment. that would be the size of the total image. Size of image, yeah, I think. So, okay, we'll leave it as that. So let's get back to this section table. So the section table, I've only got one section, which is the text section. So, but we need to loop over the section. So the section will need to contain a lot of this data, I guess, that we can just plug in. So let's just set this up. We've got characteristics, we've got number of line numbers. Then we've got the number of relocations, pointer to line numbers, pointer to relocations, pointer to raw data, size of raw data, virtual address, virtual size, virtual address, virtual size, and then name. So, okay, let's just do all of these. So this is going to be each section needs its own header here. So we've got a range over the PE sections. Okay, so we have an 8-byte field here. An 8-byte null-padded UTF-8 encoded string. If the string is exactly 8 characters long, there is no terminating null. For longer names, this field contains a slash that's followed by an ASCII representation of a decimal number that's an offset into the string table. Executable images do not use a string table and do not support section names longer than 8 characters. Long names in an object file are truncated if they are emitted into an executable file. So the section will need a name. So we'll just say name, for example, section.name. This can be a string that we convert to a byte, maybe, a byte slice. Then we'll say that if the length of name is greater than 8, then we'll just truncate it to 8. Then we'll just say for range 8 minus the len of name, we'll just append null bytes. Okay, I think that should work. So that gives us a byte slice, which we can just append. So we'll just say that this is append name onto B. So this will give us the name correctly. Then the other ones are all just offsets and sizes and things. So we'll just do this as the usual. B equals LE32, B0 or B9, whatever. So we've got virtual size, the total size of the section when loaded into memory. If this value is greater than size of raw data, the section is 0 padded. This field is valid only for executable images and should be set to 0 for object files. So this is basically going to be the padded size. So let's just do this up here. Virtual size equals padded of the len of the section data to PE section alignment. That's the virtual size. Then we've got a virtual address. For executable images, the address of the first byte of the section relative to the image base when the section is loaded into memory, so it's an RVA. I like how they defined the term RVA at the very beginning of this file and then they never use it. For object files, this field is the address of the first byte. Okay, this is object, so whatever. Otherwise, it's an arbitrary value. Okay, so basically, this is going to be whatever. This is going to be where we're asking it to load into memory. And this needs to be, I think it said that for an image we need to do it in order. So we'll just, if we're doing it in a loop, that should be fine. So the virtual address, we can't use 0. That's going to be where I assume like things like headers and stuff are kept. So we would need to go to the next alignment up. So I wonder then, let's have a look at the rest of these. So size of raw data is the size of initialized data on disk for image files. For images, this must be a multiple of file alignment from the optional header. If it's less than virtual size, the remainder of the section is 0 filled. When a section contains only uninitialized data, so the BSS section, this field should be 0. So size of raw data, we can easily fill out. Size of raw data is going to be the padded section data to file alignment. Then we've got pointer to raw data. This is, for executable images, this must be a, okay, pointer to raw data from the optional header. For object, to the first page of the section within the COFF file. Okay, so is this just the file pointer to the first page of the section within the COFF file? Okay, so this is just going to be the address within the file. So this would be, for example, if we started the code section at byte 512, this would be 512. So pointer to raw data. I guess what we'll do here is we'll just use I to figure these things out. So we'll just say pointer to raw data. This one is going to be, so we've got the size of raw data already. We're going to need to keep track of this if we've got multiple sections. So okay, what we'll do then is we'll say that pointer to raw data starts out as P file alignment. Or it starts out actually as it's going to start out as size of headers. Size of image. It's actually going to start out as this padded to the file alignment. So let's just take this calculation and put that in a const. Can I put this one in a const? Const. So we'll call this one size of headers and section headers. I think I need some better naming here. We've already got size of headers. So size of headers can be size of so size of headers, I'm just going to leave it like this and think about naming a bit later. Okay. So size of image starts with that. Then the pointer to the raw data is basically going to be the padded this constant padded to P file alignment. Then all we need to do is just after this we just need to plus equals the size of raw data, because that's already been padded, because then that's where the next raw data will start on disk, I think. So we've got a pointer to raw data here, size of raw data here, virtual address here. Virtual address I haven't done yet. But this is going to be pretty much the same thing as this. So we're going to have a virtual address. This one is going to start out as p dot, let's just say it starts out as p section alignment. Then this one will start at the first section alignment here. Yeah, I think we can just do the same calculation as this, just due to section alignment instead. And then we do the same thing. So we just plus equals the virtual size in this case, because that's also been padded to section alignment. Then we've got a pointer to relocations, line numbers, number of relocations, line numbers. These are all 0 because I don't have any of those. And then we've got characteristics. So characteristics are in the section flags here. We need to say that we contain executable code. So let's just take that one. We don't have initialized or uninitialized data yet, but we will take those as well, just for when we do have those. What else do we need? We'll need the ability to say that this section can be executed as code. And read, or read, and write. Okay. So for the code section, we'll want to say that it's a code section, and it should be executable and readable. So because I'm going to be appending these sections in the main file, this will actually just be section dot characteristics. Okay, don't need to worry about grouped sections. So I think that, you know, if we're doing pointer to raw data here, this would basically be the start of raw data. And then what I need to do is, after I've defined all of these section headers, I need to pad until the start of raw data, and then write out the sections. So we're going to need to do some kind of padding here. We'll say if padding equals... what should I do here? We're going to need to do this for each of the sections, so we'll have to loop over the sections again. So if padding, we've got pointer to raw data, which is probably worth putting onto the section. So we'll say section dot pointer to raw data equals this. And we'll just use that here. So that way we can basically say how far are we until then. So the pointer to raw data is here, the padding will be minus len of b, if padding is greater than 0, then we'll want to do b equals append b. We'll make some byte slice where we put in the padding and then just append all of those bytes. Then once we've got that, we'll just need to append any data from the section. Then it will go around to the next section, try and pad it out for that one. Okay, and then at the very end, we'll need to pad until... so we've got pointer to raw data here. This would be the start of next raw data, I think. So we would want to pad it out so that the last section has the correct amount of padding. Okay. So that means that now section needs a name. And we need characteristics, which in this case is just going to be uint32. And we need to keep track of the pointer to raw data. So pointer to raw data can be, let's see, we're using it in here, which is a 32, so we'll call this a uint32 as well. And then when I append a section, this will, for example, have the name of, let's say, text. The characteristics would be code section, executable, and read. And the data would be text, which we're generating from the code generation up there. Then we try and write it. Let's see what I've missed. So this is not constant. Okay, that's fine. I did wonder if it could be. Cannot use int as uint32. Okay, I suppose I'll just do this one as a var uint32. More uint32 stuff. Okay. Cannot use type of int as... Okay, I just have to do the conversion differently. So invalid operation on 95. These should also be uint32. Or we could just make these int, I suppose. And then where we actually use them, I'll do the conversion. So this is uint32. Okay, -1. So what did I forget to fill out? Address of entry points. Okay, so I'm saying this is the first code section, so I know now that if the section characteristics has the code flag set, then we'll set the and we'll say let's see, if base of code is 0, then we'll set base of code equal to section dot I suppose I need virtual address in here too, don't I? So this is a virtual address. And I would also want the address of entry point. So these would be up here. So a section also needs its virtual address set. So we've got pointers to raw data, we've got virtual address. Let's make these int as well. I'll leave them as uint32 and change if needed. So virtual address needs to be set, which means I can just set it here. So when we're looping over the sections, we'll have a virtual address, which is the size of headers and section headers padded out to section alignment. That's where we start it. And we would say section.virtual address equals that. Then we use that if we haven't set the base of code yet and it's a code section. Which means down here we need to use section.virtual address. And we need to add virtual size. So we may as well store the virtual size as well. So let's have virtual size. We'll set these both to uint32. Okay, let's do this here. We also need to set the virtual size. So virtual size here, this can be section.virtual size now. And we're doing the virtual size. Okay, virtual address. And that can be done in the loop up at the top here now. So this is section.virtual size. Is the section data padded to the section alignment? Okay. Let's just check this last loop. So we got virtual size, virtual address. Okay, let's see how this goes. All right, we'll just convert these here. No, actually, I do prefer just doing it, doing the conversion where they're actually used. Declared and not used address of entry points. Okay, address of entry points. That needs to be used down here. And we need a base of code. They need to be converted to uint32. Size of image and size of headers. We're not using an I as well. Okay, so size of image can be uint32 here. Declared and not used I down here. Yep, we're not using that. Okay, cannot use virtual address and virtual size, so these need to be converted to uint32. Then we've got size of raw data. And the pointer to the raw data. And then characteristics. Yeah, we'll just we'll convert this here as well. And then we're not using I down here. Okay, so now main needs to use the PE package here. So we've got PE dot on these ones. Okay, let's just try running this. Test.fin.exe. Can't run. Okay, let's just do dump bin headers on test fin. So section virtual sizes 4 kilobytes, virtual addresses 4 kilobytes in. Size of raw data 200, so that's 512, that's fine. The file pointer to the raw data, that should be correct as well. Let's see, we've got the size of stack commits, size of stack reserve. They look wrong. Size of stack reserve. Okay, let's do hex here. That should be correct. Subsystem is also unknown. Have I just done some incorrect sizes here? I forgot to change the sizes. Okay, let's go and look at the optional. Oh, okay, well, let's just look at this first. So file header values is x64 correct. Number of sections is correct. Didn't fill these out, so that's fine. Size of optional header, that should also be fine. Characteristics is relocation stripped executable. Can handle large addresses and debug information strips. So I may have just forgotten to change some of the sizes for the optional header. So we've got optional header here. Okay, let's go through this. So the optional header, we got 16 followed by 2 bytes, 16 followed by 2 bytes, and the rest of them are 32. Then we've got 8 followed by 4, 4, 2, 2. So this is 4, 4, 2, 2. These should be 16. In fact, they're all 2 down until Win32 version value, which is itself a D word. Then we've got D words until subsystem and DLL characteristics. Subsystem and DLL characteristics are 16, which are words. Then we've got stack, reserve, commit, reserve, commit. These are all 64. Then we've got loader flags, which is 32, and we've got a number of RVA and sizes, which is 32 as well. So let's try this. Oh, let's try this again. We'll go run. We'll try and do the dump headers here. Okay, so this looks much better now. Now we've got correct characteristics, Windows CUI, high entropy, dynamic base, NX, terminal server, size of image, size of headers, etc., etc. Okay, test fin.exe. It seems to be stuck. Oh. Maybe I just didn't leave it long enough. Okay, let's echo error level. Okay, we've got a completely incorrect result from this. Let's just have a look at the file. How many bytes is this? This is the correct number of bytes. 400. That should be fine for correct number of bytes. Then let's have a look at the output again. So would you go run? Okay, so we're starting off with a B9. Okay, so let's go to offset 200. Here we've got B9, 0A, etc., etc. We should end on the C3 there with, okay. So what am I actually expecting from this? So here we've got 20 divided by 2 is 10. This is 10, so it's basically 10 plus 10, 20 minus 10. So we should be getting 10 as a result out of this. So maybe I've missed a couple more fields that should be different sizes. So let's just have a look at these section flags now. So we got okay, let's have a look through these section flags. This is relocations. Where's the section data? Oh, it's here. Okay, so we've got 8 bytes for the name, which is correct. We're truncating it if needed here, and padding it if needed as well. Then we've got D word all the way until number of relocations, and line numbers should be word. So yeah, I've got the incorrect sizes here, so these should be LE16. Okay, so let's just try this again. Now we'll do test fin .exe. That looks better. So we'll echo error level. And now we get 10, which is what we expect from the program. So if I change this just a little bit, so if I just do 10 plus 25 or something, and then we run test fin again, and echo error level, now we get 35. So this is working now. So we've got a working portable executable file, 64-bit, being written to disk that we can actually run. This is good for testing the code, but right now, you know, obviously if I use too many registers and things from the last time when I was doing code generation, the entire program just crashes. So probably I'll move on to proper register allocation next, but we'll see. We'll see if anything else comes up.